All right, guys, welcome to topic 3.3 notes. We're talking about sine and cosine function values today. And really what we're going to be working with is kind of bringing the unit circle full circle, no pun intended. Sorry, that was rough. But we're going to be filling out the rest of the unit circle. We'd worked with the angle measures. Remember, pi over 6, pi over 3, pi over 2, pi over 4, all that stuff. The circle you've written a bunch this week. And now we're really getting to how do I find coordinates on the outside of the unit circle. So to this point, like looking at the graph right here, we've been working with the angle part. And now we're trying to find, like, actually, if I have some information about a point, how do I get what the point actually is? Okay, and that's where sine and cosine values come into play. And it says from topic 3.2, we know that cosine of theta is x over r, and sine of theta is y over r. And what you can do on both of these is if you multiply both sides by r, you end up with this right here. That x is equal to r cosine theta and y is equal to r sine theta. So really, if you have the radius and whatever your theta is, so I have my radius here and whatever the theta is, x is just going to be r time, like my radius times whatever the cosine of my angle is, and the same thing for sine, this one for the y coordinate, except for it's going to be my radius times sine, whatever it is. So a big thing to remember is this right here, that the coordinates of a point are given as r cosine theta and r sine theta. And on the unit circle, since my radius is just 1 for both, for the unit circle, when we get there, since the radius is just 1, it's just going to be 1 times cosine theta, so just cosine theta sine theta. But we'll get there in a second. Let's work with some examples here. So, example 1, the figure shows a circle of radius 4 with an equilateral triangle. That's important. PQO, which of the following gives the full coordinates of point Q. So I'm looking at point Q, and look at how they broke this apart. Okay, they said this equilateral triangle here, so all the angles are going to be 60 degrees, but we're not working with degrees. We don't use that. But we can think of these angles here in terms of stuff that we already know. Look at how they've broken this up. I've got 1, 2, 3. They've broken the top half of the circle into 3 portions. Let me highlight that to show you better. So 1, 2, 3. They've broken it into thirds. So here's a third, here's a third, here's a third, right? So as we know, whatever you break it into is the denominator. So right here, this like each part of this is pi over 3, right? Like they've broken this into pi over 3, 3 equal parts, because this guy right here is pi. So I split pi into 3 equal parts. And, well, if I'm looking at Q, the terminal ray of this angle is Q. So I've got pi over 3 and another pi over 3. So I know at Q I'm working with 2 pi over 3. Okay. And then it tells me my radius is 4. So writing down what we knew from above, that x is r cosine theta. So x is just going to be my radius, so 4 times cosine of whatever my angle is. So my angle for Q is 2 pi over 3. Same thing with y. R sine theta, just got to plug in twice. So 4 sine of 2 pi over 3. Beautiful. And that leaves the answer as, let me see, y'all. Let's see. So, now, if we have this, like we have the knowledge of how these work together, and remember, just for a general drawing, you can always, when in doubt, draw your triangle out and put theta here. Left to right here is in, like, left to right here is in the x direction, up and down is y, and since I'm working with a circle, my hypotenuse is going to be r, x, y, r, and then I can use SOHCAHTOA to see what I'm working with. So sine of theta is y over r, cosine of theta is x over r, and tan theta is y over x, or sine over cosine. Okay, these are just helpful ways to work with the circle. That's just a memorization trick that I've showed you all. And I draw it here specifically. Like, this is what we could have used to get, like, all of this right here, that triangle, right? But the reason why I bring it up here is because we're going to use the triangle that we have and kind of some information that they give us to find a radius. So the figure above shows a circle of radius r with the line y equals x, negative x, sorry. And the circle and the line y equals negative x intersect at points R, O, and P. And all that's saying is it's a line that goes through the middle of the circle and through these 2 points. If the coordinates of point P are 6 square root of 2 and negative 6 square root of 2, what is the value of R? So this is nice because if, like, looking at my triangle here, I know the relationships between my x coordinate, my y coordinate, and R work as this right triangle here, right? So if I ever don't know an x coordinate, y coordinate, or an r coordinate, I can do this, right? The Pythagorean theorem. So let's do that. So x squared plus y squared equals r squared. I know my x coordinate is here, y coordinate's here, so I can just plug these in. And then evaluate this. 6 times 6 gives me 36. And then square root of 2 times 2 gives me 2. So I've got 36 times 2, which is just 72. And same thing over here. The negative times the negative will cancel out. And I've got r squared. Just do the math here. And technically you would get plus or minus when you do this, but when I'm working with a radius, I'm working with a distance, and it doesn't make sense to have a negative distance. So my radius is length 12, okay? And this is just showing the relationships between my x coordinate, my y coordinate, my angles, my radius, and different ways we can work with it, okay? But really, what we want to work with is, today, what we're really talking about is, if I know theta, and I know some things about the triangle, how exactly can I get the points, okay? How exactly can I get the points? So just remember for a second that sine of theta is r times, wait, I wrote it backwards. Got ahead of myself here. Oops. That y is equal to r times sine theta. Right, scrolling back up, yep. And then x is going to be r times cosine theta. And in this example, what kind of circle are we working with? Well, the distance between the origin and this is 1, so we're working with my unit circle. So remember, when we're working with the unit circle here, if I just plugged in 1, these go away. So x is cosine theta, and y is sine theta, okay? So really what this is asking here is, how do I evaluate this based on a couple points that I have? And what I'm going to do on ones like this are, like, I'm going to fill out part of these. Like, I'll go down to a couple, and then I want you to go back into Schoology, important documents folder, and check the answer key. Make sure you can work some of these yourself. So I'm going to do a couple, leave a couple for you all to do yourself, and check your answers either with each other or on Schoology. So here's how this works. So consider the unit circle above, find the values of the following. So cosine of 0, remember the angle of 0 is going to be at point P here. So I'm just going to write that that's at point P just to help me visualize that. And cosine is just going to be my x-coordinate here. Okay, cosine is just x-coordinate there, so it's 1. Okay, let's do sine of 0. Well, that makes it pretty simple. Sine of 0 is, once again, working with point P because I'm working with angle P. And it's just my y-coordinates, so sine of 0 is 0. Now, let's do 3 pi over 2 together. So remember, if I label my circle, this is 0, pi over 2, pi, and 3 pi over 2. So if I'm working with 3 pi over 2, I'm working with s. That just helps me visualize it a little bit better. And cosine is my x-coordinate, so 0. I'm working with this right here. And then sine of 3 pi over 2 is -1. So go back and finish C, D, E, and F by yourself. A large portion of this course requires that we can find numerical values for functions involving sine and cosines at important angle values. The angles we have been working with on the unit circle involve multiples of pi over 4 and pi over 6. And because you can simplify this, like really the first quadrant is 0, pi over 6, pi over 4, pi over 3, pi over 2, but all of these can simplify, like different multiples of these can simplify to those. Now we're going to put several ideas together from everything that we've been doing so far to help us with this task, okay? And I know this looks like a lot, but consider this unit circle above with an equilateral triangle inscribed inside the circle. The angle theta, so right here, shown above, will have a measure of pi over 6, which we know. So we've been writing it out here, which can cause a little bit of confusion, but what we've been talking about the whole time is that pi over 6 is this angle inside. Pi over 6 is this angle inside. We can see that the y-coordinate of point P is 1/2. Okay, we can see the y-coordinate of point P is 1/2. So we can go ahead and write that down if we want to. We can use the Pythagorean theorem to find the x-coordinate. So if we know, because it's an equilateral triangle too, like how do we know it was 1/2? Well, right here, this radius is 1, so 1, 1. So all the way across is 1. So that's how we're getting that this part of this triangle, like if I turn this into a right triangle here, let me highlight that. This right triangle I just highlighted would take half of that, so that's how I get the 1/2 there. And then, once again, you use Pythagorean theorem. X squared plus y squared equals r squared. My r squared is going to be 1 squared. I don't know what x squared is. And my y squared is going to be 1/2 squared. So if I evaluate this, that gives me 1/4 equals 1 minus 1/4 on both sides. I have x squared equals 3/4. And remember, when I take the square root on both sides, with a fraction like this, you can take the square root of the top over the square root of the bottom. Square root of the top over the square root of the bottom. So the top will not simplify, but the bottom will. And realistically, this should be, anytime I take a square root, what do I got to have? Plus or minus. And then I just see what quadrant I'm in to tell if it is plus or minus. Because this is going to be my x-coordinate here. And because I'm in quadrant 1, this is quad 1, I can say that this confidently that this should be positive square root of 3 over 2. Okay, that's the long way. Today's lesson really is talking about why are the coordinates what they are. Like, how do we find them brute force? Really, skipping ahead a little bit, don't follow me, but what we're really going to do is just memorize this, okay? We're just going to memorize this. This is going to make life a lot easier. There's an easy way to do this, but I want you to see why before we actually do anything with it, okay? And that'll and that'll help out. So, and if I look at this right here, I can say, so I know my theta is pi over 6. So remember, sine of, well, like, let me go back just 1 second here. And in the unit circle, I know that x is, oh, not writing. X is cosine theta, and y is sine theta. So I can say that for this, cosine, like writing it the way it is, square root of 3 over 2 is the value for cosine of my x value. So cosine of my angle gives me that, okay? And then if I plug in my y coordinate, so just by knowing these coordinates, I can quickly know that the sine, like if I plug in pi over 6, because remember, sine is a function here. Like if I plug in something to sine, it's going to give me something out. And if I plug in sine of pi over 6, it's going to be 1/2. And if I plug in right here, if I plug in pi over 6 into cosine, it's going to spit out square root of 3 over 2. And this is going to be useful, and we'll see it here. And notice we found two values of x when solving the Pythagorean theorem. This is just talking about the fact that there's quadrants, and we can use symmetry to repeat around the circle. And the Pythagorean theorem plays an important and interesting role in trig functions, and we're going to use it a lot. So, long story short though, the figure shows the unit circle with an equilateral triangle. Use the symmetry to find these above. So, once again, look at just what the chart gives you. The chart tells me that at P, this is pi over 6, right? Pi over 6. So, when it makes these equilateral triangles, I know my base, like the numerator, not the numerator, sorry, it's an early morning. The denominator on all my fractions is going to be over 6. It's going to be something pi over 6. It's going to be something. And that's where, yes, you could go through and work through how all these angles work and the facts of the equilateral triangle, but if you just have your radian measures, you can fill this in this quick, right? Like you all know this. You all know this, right? Like you all know that that's 5 pi over 6 now, and that's 7 pi over 6. Like we can work through that quickly. So we can go ahead and fill that in. All right, and then if I know the coordinate of one, I know the coordinate of all of them, right? Because they're in equal spots. They've just been shifted left, right, up, or down. So over here in quadrant 2, all that changes is that my x value is going to be negative. Down here, my y value becomes negative as well. And then over here, if I'm shifting down from this or over from this one, it doesn't really matter which way I think about it. But I have a positive x value and a negative y value, right? That's just using my quadrants. So really, just like how when we were memorizing the pi over 6s and the pi over 4s and all that stuff, once we know this top right quadrant, I can tell you the rest of the unit circle because it just repeats, okay? So you can fill in these values, like all these values here, and fill in your chart, okay? So, now, just as we did for the notes in pi over 6, we can do the same thing for pi over 4. So, same way here is that we can draw pi over 4s here, and it shows in this chart here exactly how they're getting the angle measures that they are, or the radius measures that they are. This is a special right triangle. I'm not going to bore you with that. We're just going to kind of brute force our way to do some of this. But what we do know is that if this is pi over 4, these are going to be over 4s. And you all know these by now. So 3 pi over 4, this is 5 pi over 4. Because they have this kind of symmetry, right? And 7 pi over 4. Right, we're getting quicker with being able to write these down, and I can quickly tell a lot of things about them. So same thing works here. If I know one of the coordinates, like basically we're going to try to memorize this side over here, and then I can tell you the rest, right? So I can go over here, point Q, the x becomes negative. And then just use the same symmetry and just my quadrant rules. My y becomes negative as well. And then the only one negative over here, let me draw that again. The only one negative over here is my y coordinate. Okay, and that's what you're using to fill in this chart here. Okay, so use the angle measures and fill in the chart just like we did. Same thing for pi over 3. It shows exactly how they're doing this. It says equilateral triangles once again, and like for this equilateral triangle, they're going halfway, they're doing half of the radius. And then you can use the Pythagorean theorem to find that that's square root of 3 over 2. We did that a little bit earlier. I'm not really worried about finding that for now. Like if you want to talk more on Monday about how that actually works and the why and the what behind it, I can give you videos. I can give you more time. But just for the sake of time here, we know that this is pi over 3, right? Like we know that this is pi over 3. And this is 2 pi over 3. This is 4 pi over 3, and then 5 pi. And really it's talking about, so for 5 pi over 3, just remember, I'm going to draw it in blue here. For 5 pi over 3, I'm starting here, and then it's the angle that terminates at S, okay? So, and then, once again, once you know this one here, you can get the rest. X becomes negative. Y becomes negative. And then okay. And this is the unit circle that I've been mentioning, right? And I'm going to point out a couple things. Like now we have all of these, and this is how you would draw it from now on, right? Like you have the radian measures right beside the coat, like where they terminate. So like pi over 2 is right there, pi over 6 is right here, and I have these coordinates here, right? And then all of these just repeat. All of these just repeat. So all the way around, and they repeat with the same, the nice thing is not only do they repeat the same coordinate values, but they go with the same denominator in the fraction. So pi over 3, 2 pi over 3, all my over 3's, look at them. 1/2 and square root of 3 over 2, and it's just different variations of the same point, just different y and x values as far as the signs go. Okay, so once we know all of them in quadrant 1, we can just find those. And one thing I do want to point out is that at like the halfway points, I'll highlight these in green. Like my pi over 2, pi, 3 pi over 2, and 0 or 2 pi. It's just it's just like a normal coordinate. So if I go a radius of 1 here, I went over 1 and up 0. Up here, I went right or left 0, and I went up 1. That's how I'm getting these values. And then here, I went left 1 and up 0, okay? And then obviously down here, I went right or left 0 and down 1, okay? So we're going to work with this more, especially on Monday. I'm going to let you work through a worksheet packet, and then on Tuesday, we'll work on different patterns that you see to memorize it. One thing I do want to point out, just the general, like getting comfortable with this, notice here, if I draw originally that this is 0, 1, and 1, 0, look at the x coordinates. It's all over 2, like the x and y coordinates. That's easy to remember. And look, it's just the square root and counting up from 1. So square root of 0 is 0, square root of 1 is 1, square root of 2 is square root over 2, and square root of 3 is square root of 3. And then it goes backwards. 1, 2, 3. Make sense? And now, here is what I would want you to do. The unit circle shows some different values in quadrant 1. I want you to use these values to find values that you don't already have. So sine of 2 pi over 3, for example. You would have to go in here. I would start by labeling the angle. So this is 2 pi over 3 right here. And I know that that would be negative 1/2 and square root of 3 over 2, because I look at the ones that are also pi over 3, and that angle moves over. That coordinate is the same over here, just with a negative x. And then remember, x is cosine, and y is sine. So when I'm looking for sine on A, I go to 2 pi over 3, and the y coordinate is square root of 3 over 2. Square root of 3 over 2. Okay? And for another example, 11 pi over 6 would be right here. And then that's pi over 6, so my pi over 6 goes with 11 pi over 6, and all that changes is that my my y coordinate is now negative. And if I'm working with cosine, remember cosine is x, so it's just my x coordinate, which is square root of 3 over 2. Now, I want you to finish this page and any other examples or things I skipped over, and then you're done.